Last time we discovered why linear algebra came into existence. For centuries, mathematics had an incredibly successful language. That language was built on numbers. With numbers, we could count objects, measure distances, compare quantities, and describe the world with remarkable precision. If I tell you there are 7 books on this table, the number 7 communicates everything you need to know about a quantity. If I tell you a rope is 10 meters long, that number 10 completely describes its length. Numbers answer a very important question: how much? For a long time, that question seemed sufficient. But as mathematics begin to describe geometry, motion, and eventually physics, a problem quietly emerged. Imagine I tell you that car traveled 5 kilometers. Have I completely described its motion? Not quite, because 5 kilometers in which direction? Did it travel north, south, east, or west? The number tells us how far the car moved, but it tells us absolutely nothing about where it moved. That missing piece of information turned out to be essential. The same distance can produce infinitely many different motions depending on which direction in which it is measured. So, although numbers were incredibly powerful, they were fundamentally limited. They describe magnitude. They don't describe direction. And once mathematics begin to study objects moving through space, that limitation becomes impossible to ignore. A richer mathematical language is needed, one capable of describing not only how much, but also which way. That new mathematical language is called a vector. The word vector is introduced very early in mathematics. Yet, it is also one of the most misunderstood ideas. Many students encounter vectors for the first time as an arrow drawn on the page or as columns of numbers inside brackets. Those representations are useful, but they often hide the central idea. A vector is not simply a more complicated number. It belongs to an entire different category of mathematical objects. Where a number measures only magnitude, a vector combines two independent pieces of information: magnitude and direction. Neither of these two are more important than the other. Together, they define the vector. That simple addition direction changes everything. It allows mathematics to describe motion instead of just distance, force instead of just mass, velocity instead of just speed, and electric and magnetic field, fluid flow, computer graphics, robotics, navigation, and even artificial intelligence. Everywhere mathematics need to describe quantities that both have size and orientation, vectors appear naturally. This is why linear algebra begins with vectors. Not because they are convenient, but because they are necessary. Without vectors, mathematics can measure the world. But with vectors, mathematics can begin to describe the geometry of the world itself. If vectors are not numbers, then another question naturally follows. What do they actually look like? Mathematics is a visual language. Whenever possible, we try to represent abstract ideas with pictures that capture their essential properties. For vectors, the most natural representation is an arrow. This choice is not arbitrary. Every part of the arrow carries meaning. Its length represents the magnitude of the vector, and the direction in which it points represents its direction. Together, these two properties completely describe the vector. Nothing else is required. At first glance, it is tempting to conclude that the arrow itself is a vector, but that is not entirely true. The arrow is only a representation. The vector is the mathematical object that the arrow describes. This distinction is similar to the relationship between a word and the idea it represents. Consider the number 5. The symbol 5 is not the number itself. It is simply a way of writing the concept of 5. If we write the same quantity as V, 5, or Chinko, the underlying idea has not changed. Only its representation has. Vectors are no different. An arrow is simply one language for expressing a vector. In fact, the same vector can be represented in many different ways. As an arrow, as a column of numbers, as a row of numbers, or even an algebraic expression. All these are representation. The vector itself exists independently of how we choose to describe it. Understanding this distinction is more important than it may first appear. Because one of the most common mistakes beginners make is confusing the representation with the mathematical object itself. Throughout this course, we will continue to separate the two. We will distinguish the mathematics from the notation, the idea from the symbol, the object from its representation. And that habit will make the more advanced ideas in linear algebra much easier to understand. In the next section, we will examine the consequences of this decision that surprises almost everyone the first time they encounter it. Can the same vector exist in different places? Now that we understand why arrows are used to represent vectors, can we ask a more subtle question? Where is a vector? Suppose I draw a arrow here. Now, suppose I erase it and draw the exact same arrow somewhere else. Has the vector changed? At first, it may seem obvious that it has. After all, it's now in a different location. But look more carefully. Its length is exactly the same. Its direction is exactly the same. Nothing about these two defining properties has changed. Only its position has. And this leads us to an important realization. A vector is not defined by where it is drawn. It is defined by only its magnitude and its direction. Its position is irrelevant. This may feel strange because we naturally associate arrows with the place where we see them. But mathematics asks us to separate objects from the picture. The picture may move, the vector does not. As long as an arrow keeps the same length and continues to point to the same direction, it represents exactly the same vector regardless of where it is placed. For this reason, mathematicians often slide vectors around freely. This operation is called translation. Notice that we are not rotating the vector, we are not stretching it, we are not changing its direction. We are simply moving it through space while preserving everything that makes it a vector that it is. Because of this freedom, there is one location that becomes especially convenient: the origin. Whenever we compare vectors, perform calculations with them, or describe them using coordinates, we almost always place them so that they begin at the origin. This is not a mathematical requirement. Nothing in the definition of a vector says it must start there. The origin is simply the most convenient reference point. It gives every vector a common starting position, making them easier to compare and easier to describe. This simple convention will become increasingly important throughout this course. Almost every vector you see from this point forward begins at the origin. Not because vector belongs here, but because it allows us to focus on what truly matters: their magnitude, their direction, and the geometry they describe. In the next section, we answer another important question. If vectors are not numbers, then why do they often write them as clumps of numbers like this? What do these numbers actually mean? By now, we have established two important ideas. A vector is not a number, and a vector is not the arrow we use to draw it. But there is one misconception that almost every student encounters. It appears the moment coordinates are introduced. Suppose we place a vector at the origin. From there, it's moved 2 units to the right and 1 unit upward. Instead of describing that movement with words every time, mathematics give us a much more compact notation: 2, 1. Most textbooks introduce vector this way. And because of that, it is easy to begin thinking that these columns of numbers is the vector. But it's not. These numbers are simply a description. To understand why, consider something familiar. Imagine you have a house. Your house has an address. Perhaps it is 25 Maple Street. That address tells other people where your house is located. But the address is not the house. You could write the address on a piece of paper, you could type it into a computer, you could even translate it to another language. The house remains exactly the same, only its description changes. Coordinates play the same role with vectors. They tell us how to locate a vector relative to a chosen coordinate system. Nothing more. The vector is the object. The coordinates are simply one way of describing that object. This distinction became even clearer when we changed the coordinate system itself. Imagine rotating the axis or choosing the axes that are no longer perpendicular. The vector has not moved. It still has the same magnitude and still points in the same direction. Yet, the numbers that describe it are now different. The coordinate changes because the language we use to describe the vector changed. The vector itself did not. This is one of the central ideas of linear algebra. Vectors are geometric objects. Coordinates are merely their representation within a particular coordinate system. And throughout this course, we always keep those two ideas separate. Because once you understand that a vector exists independently of its coordinates, many of the deepest ideas in linear algebra begin to feel surprisingly natural. In the next lesson, we'll take our first step toward working with vectors. If vectors represent quantities in space, then what should it mean to combine them? In the other word, what does it really mean to add two vectors? In this lesson, we began with a simple observation. Numbers are powerful. They allow us to count, measure, and compare quantities with remarkable precision. But numbers alone cannot describe the geometry of the world. They cannot tell us which way something moves. To overcome that limitation, mathematics introduced a new kind of object, a vector. Unlike a number, a vectors combine magnitude and direction into a single mathematical idea. Although we often draw vectors as arrow, the arrow is only a visual representation. And although we often write vectors as columns of numbers, those coordinates are only one way of describing them. A vector exists independently of both. This distinction may seem subtle, but it is the foundation upon which all of linear algebra is built. Everything that follows in this course, vector addition, scalar multiplication, linear transformation, matrices, determinants, eigenvector and eigenvalues, and even higher dimensional space depend on understanding what a vector truly is. If this single idea is clear, the rest of the subject becomes far more intuitive. If it's not, every new topic feels like another collection of symbols to memorize. That is why we spent an entire lesson on what appears to be a such simple question. Because in mathematics, the deepest ideas are often the simplest one. In the next lesson, we will move beyond individual vectors and ask our first operational question. If a vector represents a displacement in space, what should happen when we combine two of them? Can vectors be added in the same way that numbers are added? And if they can, what does that addition actually mean geometrically? That question will mark the beginning of our journey from simply understanding vectors to learning how to think with them. If you like this, make sure you like and subscribe for more, and I hope to see you on the next lesson.